Last time we learned how to calculate the magnetic field of a current-carrying wire by using the Biot-Savart law. This lets us calculate the magnetic field created by a continuous distribution of electric current, and it's really analogous to Coulomb's law for electric fields. These two equations are really all that you need in order to calculate electric and magnetic fields from any distribution of charge or current that you can possibly imagine. However, as we discovered with electric fields, that making use of symmetry could often dramatically simplify a calculation, the same is true for magnetism. Coulomb's law and the Biot-Savart law are kind of brute force methods. They are the fundamental relationship between charge and current in electric and magnetic fields, but they don't intrinsically make use of any symmetries or anything like that, and so they can often be a lot of work to actually use in practice. If we want to calculate the electric field of a symmetric distribution of charge, it's often easier to use Gauss's law. Luckily, there's an analogy for Gauss's law for magnetism, and it even follows essentially the same mathematical form, and we call it Amperes Law. Unfortunately, the derivation of Amperes Law from the Biot-Savart law is quite complicated, so I'm not going to be able to prove it to you. However, for those of you who are curious, you can get to Amperes Law from the Biot-Savart law by making use of a mathematical theorem called Stokes' theorem. So now let's talk about what the different parts of Amperes Law mean and how we actually use it in practice. First of all, this little loop thing means that we have to integrate over a closed contour. So we have to integrate over a line or a curve such that we end at the same place that we began. This contour is called an Amperian loop, much like we called the surfaces in Gauss's law Gaussian surfaces. Before we can actually do anything with this, note that ds, which represents the little pieces of our loop, is a vector, which means it has a direction. So we need to choose a directionality of our loop. Conventionally, we choose the counterclockwise direction. It basically goes along well with our right-hand rule. However, in practice, it is often convenient to choose the direction of your loop so that B and ds are in the same direction as each other, if it's possible to do so. Next, what do I mean by enclosed current? Unlike with Gauss's law, we don't actually have a fully enclosed 3D volume where a charge is like inside it or not. But what I mean is current that passes through this loop. So imagine that there are wires going into and out of the screen that you're looking at, each with their own currents and directionality. The currents that pass through our Amperian loop are the enclosed current within the loop. And so in this case, Ampere's law tells us that the loop integral of B dot ds is equal to mu naught times the sum of all the enclosed currents within our Amperian loop. And here again, there's the convention that currents going out of the page are positive and currents going away are negative. This is once again corresponding to the right-hand rule. If you stick your thumb out of the page and you think about the magnetic field that a current in that direction would create using your right-hand rule, your fingers would curl around counterclockwise, which is consistent with this direction here. To compute the integral on the left, well, we have to compute B dot ds at every point around the loop. In general, that's really hard to do. Just like Gauss's law in general is really hard to compute. However, when you have symmetry, this integral simply becomes a product, and we can multiply it by a constant value of the magnetic field times the total length of the loop. So again, Ampere's law is meant to make your work easy when you have a good deal of symmetry to work with. It dramatically simplifies calculations when you have symmetry, and it makes everything harder when you don't have symmetry. The simplest example that we can use Ampere's law in is for a long straight wire. To use Ampere's law, we need to come up with an Amperian loop that makes our integral easy to compute. We need to make sure that our loop encloses our wire so that the right-hand side isn't just 0. And we want to make sure that B dot ds isn't really changing along our loop. The easiest way to do that is to just pick a circle centered around the wire, because we know that the magnetic field created by this wire is itself in circular patterns. So at any particular distance from the wire, the magnetic field has a uniform strength, And as you go around, it's only the direction that changes, which means we can replace this vector b and this vector ds with a product of the magnitude of the strength of the magnetic field with the circumference of the circle of our circular Amperian loop. Rearranging this expression a little bit tells us that the magnetic field created by this wire at a distance r is equal to mu naught times the current of the wire divided by 2 pi r. And you'll notice that this is exactly what we found by using the Biot-Savart law last time, except this was a fraction of the amount of work. We didn't have to worry about trig substitution or actually really even evaluating an integral. We replaced this integral with this product. Once in a while, we might not be able to convert this integral into a product so quickly. For example, if we have a loop that's a bit of a funny or complicated shape, we might have to break this integral up into pieces. But generally speaking, what we would do is we would say, well, this is an integral of b over our loop, but we're choosing our loop so that b is constant, which means we can pull it out of the integral. And now we're simply integrating ds, the length element of our loop, over the entire length of the loop. And so we can plug in our bounds, which in this case are 0 and 2 pi r, and our integral simply becomes 2 pi r. A somewhat more complicated example is of a long, thick wire, where the diameter of the wire is thick enough that we have to consider the fact that the current is kind of spread out. In this case, it's reasonable to assume that the magnetic field will look different inside the wire compared to outside the wire. So if we do this inside the wire, we want to draw an Amperian loop at a radius smaller than the radius of the wire itself, so that we're really probing what the magnetic field looks inside the actual wire itself. Assuming that the current is uniformly distributed throughout this wire, then the ratio of the current enclosed within this loop to the total current through the wire is equal to the ratio of the surface area of the cross-sectional area of our Amperian loop to the surface area of the cross-section of the entire wire. The left-hand side of Ampere's law, the integral, is going to be exactly the same as it was the previous time. Because we still have the cylindrical symmetry of a wire, we can expect the magnetic field to continue to have this sort of circular looping behavior. Putting these two things together gives us a magnetic field that increases the farther we get from the center of the wire, so long as we remain inside of the wire. This is basically the same as the electric field inside of a cylinder of charge. Outside the wire is a little bit easier. This time we draw our Amperian loop on the outside of the wire. All of the current in the wire is enclosed, and the integral on the left-hand side remains the same. And so this is basically just the example of a long, straight wire. Combining these two, we can define the magnetic field of this wire everywhere, both inside and outside, and we see that at the very center, it's equal to 0. There's no enclosed current within our loop. And as we move farther and farther away, the magnetic field increases linearly until we reach the edge of the wire where it starts to fall off as 1 over r. A very practical application for this is in a coaxial cable. In a coaxial cable, current flows in one direction through an inner core. Then there's a layer of insulation, and then a ring of conducting material where current flows in the opposite direction, surrounded by another layer of insulation. To some extent, this is how most or even all power cables operate. We don't have one cable for current going into a device and a separate cable for current going out. The same cable contains in and out. Now, in some cases, the wires are stranded, so they're kind of wrapped around each other instead of nested like this. But there's a particular reason why a coaxial cable is used for a lot of scenarios where you're using very high currents. You typically don't want your electric cabling to produce strong magnetic fields. But if you have a whole bunch of current flowing through a wire, it's going to make a big magnetic field. However, if you use Ampere's law outside of the inner core, only the inner core's current would be enclosed. The magnetic field in this region would be the magnetic field of a current-carrying wire with a current I. If you have an equal amount of current running out the other way in the wire, then if you use Ampere's law outside that second cylinder, the enclosed current is actually zero because the two currents are opposite directions, which means outside of this cable, the magnetic field will be effectively zero. This is especially important if you have a cable with a lot of current running through it next to wiring that's carrying information. The strong magnetic field of your power cable could interact with the current through the data cable, which could actually affect the signal that you're trying to send or receive. I'm not going to work through this whole example, but this is a good kind of problem to work through to make sure that you understand how Ampere's law works. The last thing I want to talk about are solenoids. This is an image of an actual solenoid, which consists of a wire that is looped around in a coil. The reason why we bother giving these a special name is because they're extraordinarily useful. And the primary reason why they're useful is that it turns out that they have effectively the same magnetic field as a bar magnet, except it's determined by the electric current through it. That means you can vary the strength of this magnet just by changing the amount of current through it, and in fact we can make much more powerful magnets this way than we can with permanent magnets. We can even reverse the polarity of the magnet by switching the direction of the current we pass through it. So basically we get a bar magnet with way more control and a much greater range of fields. Trying to compute this magnetic field using the Biot-Savart law would be next to impossible, at least to do by hand. The wire is looping around, the direction of the current is constantly changing. It would be really, really hard to do. You could do it numerically on a computer, but you'd never be able to actually compute this integral by hand. Luckily, Ampere's law will save us. So first what we're going to do is we're going to kind of cut away, not in reality, but just visually, the parts of the wire that are looping around. We're going to look at a cross-section of our solenoid. At the very top of the solenoid, the current is coming towards us. These are little plus symbols. On the very bottom, the current is going away from us into the screen. It's very blurry, but these are our little minus signs. If you think of the magnetic field created by just this little bit of current at the top from one of these little wires, it'll be a counterclockwise circular field around the wire. But the same would be true of the one just to its right. And you'll notice that where these two loops overlap, the magnetic fields are going opposite directions. The left magnetic field is pointing upwards, and the right magnetic field is pointing downwards. And that means that sort of along the length of where these are all lined up, along the top of the solenoid, their magnetic fields cancel out with each other. On the other hand, just to the bottom of this row of wires and just above, they add up to each other. And so the magnetic field inside is going to be pointing to the right from all of these, and outside it would be pointing to the left. Because the current is moving in the opposite direction through the bottom wires, their magnetic fields will circulate clockwise. They will once again cancel each other out sort of in between, but above them the magnetic field will once again point to the right, and below them it'll point to the left. In other words, the magnetic field inside the solenoid will point to the right as a consequence of all of these little wires. And outside the solenoid, it'll actually be a very small magnetic field, not zero, but if our solenoid is very, very skinny compared to its length, then outside is going to be almost zero because the magnetic field over here will be left from these two and right from these two, and they will cancel out to a large extent. And the farther we get from the solenoid, the better, or the more precisely they'll actually cancel each other out. To calculate the magnetic field, we can draw an Amperian loop, because if we make the assumption that our field is essentially zero outside and that it's pretty much uniform inside, then a square loop like this becomes pretty easy to calculate. Because our magnetic field isn't the same over the entire Amperian loop, we're going to have to do our integral piecewise. This first integral gives us the strength of the magnetic field times the length of our Amperian loop, because the magnetic field is always pointing the same direction, and based on our assumption of a long, skinny solenoid, the magnetic field will be essentially uniform inside. So the first term just gives us B times L, which is the length of our loop. Along the side of our loop BC, while we're still inside the solenoid, B points to the right and ds points upwards, and they're perpendicular, and so the dot product is 0. And then outside of our loop, we're making the assumption that our magnetic field is essentially 0. And even if it wasn't 0, it would be pointing to the left, which would still be perpendicular to ds. And so the second term cancels out. It's 0. The third term, again, under the assumption of an ideal solenoid, where it's very skinny and very long, the magnetic field along from C to D is essentially 0, because the components from these wires and these wires cancel out. That means our third term is going to be 0 because B is essentially 0. And our fourth term, once again, B and ds are perpendicular to each other, and so that's also going to give us 0. And so this integral is simply the magnetic field inside the solenoid times the length of our Amperian loop. Then, by applying the rest of Ampere's law, we see that this has to be equal to mu naught times the enclosed current. And the enclosed current is simply the number of wires inside of our loop times the current through each of them. And since, again, each of these wires are connected to each other, they're a continuous sort of coil, their currents are going to be the same. This tells us that the magnetic field inside of a solenoid is equal to mu naught times the current through the solenoid times the number of loops of the solenoid divided by its length. And we often write the ratio of the number of loops of the solenoid divided by its length as a lowercase n, just to simplify things. So just to recap a little bit, if you have some strangely shaped wire with current running through it, or the current is varying from place to place, BOS of R will get you the answer, although it might be a great deal of work. On the other hand, if you have a scenario that has symmetry, typically some kind of cylindrical symmetry, then Ampere's law can dramatically simplify your calculations. You have an integral that very quickly stops being an integral, and then you simply count up the current that passes through the loop that you've chosen.